So now that we've kind of covered that, that sound is vibration and vibration is sound, how is it that our ears are able to distinguish different sounds? Well, and this is kind of where the cool, fun part kind of comes in. But in establishing that sound is frequency and frequency is pitch, basically every sound that we hear, fundamentally at its fundamental level, has a frequency or a pitch. But what happens is that as different frequencies are added to the mix, different sounds are created. As you stack simple sound waves on top of each other, they become complex, and our ears don't hear the complexity, they just hear table, couch. If I were to play a piano, they'd hear piano. But it's just a different arranging and stacking of simple sound waves, which simple meaning this, simple wiggling. If I were to take my hand and put a pencil on it and run a paper across it, you'd see kind of a pattern that looks a little bit like that, kind of going up and down in a circular way, and we call that a sine wave. And a sine wave it's the building block of sound. It's the building, every sound that we hear is some level in variety of that pattern that we see. It's a mathematical term. It's from cosine, and for sound, it is the equivalent of an atom. It's the foundation point. You can't break any sound lower than that. So we're going to delve into that a little bit further. But so the complexity of sound is built up of a bunch of simple sounds added together to create complex sounds. So we're going to start with the simple sine wave. Okay. So let's take a tuning fork, for instance. Kind of what they look like. It's got the prongs, and you used to have them in band or choir, and they were orchestra. They tap it, and that's where everybody got their master pitch. Well, the interesting thing about a tuning fork is that it operates on a single frequency, and they're tuned to that frequency, so they're designed in such a way. But when you strike it, again, you see the prongs moving back and forth, and with the prongs moving back and forth, it's pushing those air molecules in such a way that it's producing these compressions of air, and then this other thing of squeezing and pulling them back, which we call a rarefaction. But it's the pushing and expanding of the air in that smooth sine wave pattern. And what also happens when we hear that pitch. So you might have tuning fork A that is tuned to a middle C, for instance, and you would hit it and you'd hear a middle C, and it would be vibrating at X and X speed. Okay, if I were to take a tuning fork that's maybe a little bit longer, maybe tuned to a G below that, it would be longer. When I would strike that one, it would still do the sine wave pattern, but the pattern would be slower because the vibrations are slower. So again, when we talk about frequency, we're really talking about the speed of those oscillations, the speed of those vibrations. And that's why in pitch, and I didn't know this for years, there's always in tuning, there's always a number associated with tuning. Like the Western tuning, for instance, is 440. Well, basically what that means is that when we hit an A on our piano, that particular A, the frequency of that A is 440 hertz, which is 440 vibrations per second, producing that note. And there are other scales that use a different scaling. But basically, if you begin to dial down that 440, 439, 440, 438, 437, at first you wouldn't hear any pitch difference, but as you dial that number down, you begin to hear that pitch go down. The thing to know here is that all sound is pitch. But then what we have also occurring in nature are sounds that don't sound to our ears like pitch. Like when I hit this table, I don't hear pitch. The reason why is because the frequencies that are represented in this table are kind of not mathematically, they don't make any sense mathematically, and so we're getting a bunch of pitches all simultaneously, which sounds more like noise. That is a noise as opposed to a pitch. So for instance, if I were to take a cymbal and strike that cymbal, what you would hear would be more of a psh kind of sound, right? And that's because the way those frequencies are distributed and vibrating, they're kind of all across the board, across the spectrum. And when we hear a splattering of frequencies across the spectrum, our ears don't hear that as thousands of pitches played at the same time. It hears it as cacophony, as noise. Right? Okay, so now let's talk a little bit more about this periodic thing. Like, what are we talking about with periodic sound waves? Let's take, for instance, a string, like a guitar string or a piano string, and I were to tighten that string up to a particular frequency, meaning that when I whack it, it's going to produce enough vibrations to play a specific frequency, therefore a specific note. Here's what's happening. You're getting your primary frequency, which is our sine wave. It's moving in this pattern up and down. If I were to take a pencil and glue it to it and move a paper along, it would draw a sine wave. But in addition to vibrating up and down like this, it's also dividing itself in half and vibrating like that. Like that. I can't really do it. But it's dividing in half. And what happens there is the fundamental frequency, let's just say for our intents and purposes that it's playing a frequency of 100. Once you divide that string in half and it vibrates this way, you've cut that frequency in half. So now it's playing a frequency at double the first one, because it's, cut something in half, it doubles it, right? So it's playing the primary frequency of 100 hertz and now a secondary frequency of 200 hertz. But what also happens is that when you cut that string in half, it's playing that 200 frequency at half the volume. So it's doubling the frequency and it's lowering the volume to about half. And this is oversimplistic. Not every string responds quite this way, but for the sake of describing harmonics. Then, to make things even more interesting, that string divides itself again into thirds, and it's also vibrating in thirds. And it's playing another frequency above the first two that is 3 times the frequency of the primary. So now it's playing a frequency at 300 hertz at an amplitude, at a volume level of 1/3 the primary. So as you can see, the frequencies go up in mathematical intervals and the amplitude goes down in mathematical intervals. And all this is happening all at the same time. And this is where we have what we call timbre or harmonics. As each harmonic is played at greater mathematical interval frequencies or periodic frequencies with decreasing volume, our ears don't hear all those individual pitches. What they hear is harmonics. And that's what gives us the color and the quality of an instrument. And that's how we know a piano is a piano, and how a guitar is a guitar, and how a violin is a violin.